right, so we've looked at a lot of detail regarding translational motion or linear motion, motion along one dimension or even two dimensions with projectile motion. And a lot of the rules that apply to constant velocity and constant acceleration in the linear world also apply in the rotational world. So we're going to spend a little bit of time talking about rotational kinematics and rotational motion and how what we've already learned can apply very well to our rotational kinematics. All right, so when we talked about translational motion and translational kinematics, we introduced some players of motion. And we introduced those with some questions. And one of those questions was, how far? And how far in the translational world, you will recall, was a position, right? Or a change in position, a delta x. And x was our variable for position. All right. Well, how far in the rotational world is exactly the same in terms of how far along something rotates. So if we imagine a turntable, I'm going to do kind of a top-down view of a turntable. So here's our turntable. All right, it's rotating about an axis at the center. And an object is spinning around on this turntable. So let's say we have a nice little square right here. And if I were to map its trajectory as it moves around this turntable, as it rotates around the turntable, if I talked about how far something is rotating around this turntable, how might we answer that question? Well, we actually have two ways to answer that question, right? We have the length. If I took a string and I mapped out this entire rotation of this thing on a string, and then I stretched that string out and measured the length, well, that's how far the object rotated. So how much is that? How far is that? Well, that is what we call the arc length. And for one rotation, the arc length is the circumference. Okay, so the circumference of a circle, the distance around that circle. And the circumference we know as 2 times pi times the radius. All right. Well, what's another way that we can talk about it? Well, we can talk about it as making a complete circle. One rotation. And a full circle is 360 degrees. So we can also talk about the distance as an angular, angle theta, an angular distance. Now, as it turns out, we don't actually operate in the degree world. We operate in the radians world. And 360 degrees in radians is 2 pi radians. So this actually gives us a relationship between a rotation, one rotation, and how far that is in radians. And we find that the arc length, if I only wanted to do part of the circle, and a little back to our geometry, this is where the arc length equation comes from. So if it only travels that distance, the length it travels, we're going to use the variable s, the length that travels s is equal to the angle in radians times the radius. This is our arc length relationship, geometrically, what the arc length is. Well, how does that relate to our situation here when we looked at a full circle? Well, let's look at that. So for a full circle, the angle it goes through, 2 pi times the radius, gives me the arc length, which is the circumference. So it works, okay? So if I want to determine the distance, the translational distance, the how far, in rotation, I need to know what the angle is that the object goes through times the radius. Okay, so this is our how far question. and how we get how far an object moves. The how far in this is in, of course, arc length. Well, we have that as an arc length. We can also just think of how far as the angle that the object travels through, if I'm talking purely in rotation. So if I need to know lengths so that I can do determinations of length, then we have to go to the arc length. If I'm just looking in the rotation and how far the object does in terms of its rotational language, I can just keep the angle. So it makes 2 pi radians. It went through 2 pi radians of rotation. It went through 2 pi radians times the radius in terms of the length. All right, so that's the how far piece, relating translational motion to rotational motion. But we also talked about how fast. So let's talk about how fast a little bit. Well, we can ask ourselves sort of the same question. How fast really is how far divided by how much time, right? So that was our sort of generic conceptual how fast idea. How far in the amount of time that it travels. So we have to decide if we want to talk about how far in terms of length or how far in terms of rotation. All right, let's talk about rotation first. So for rotation, we call this omega, or lowercase omega, angular velocity. How much rotation I get in the amount of time. How much rotation I get in the amount of time. If I want to talk about linear velocity, I'm talking about a very specific type of linear velocity in this case. I'm talking about the velocity, so our linear velocity, right at the point, the linear velocity at this point in time is the velocity tangential. Now, we talked about tangential velocity when we did two-dimensional motion, projectile motion, right? So this is where it's going to come in again, different use right now. But we're thinking about the tangential velocity. What is the linear velocity of that object at the instant I'm examining it, at the time I'm examining it? So how is linear velocity related to angular velocity? Well, we can use our example of one rotation again. We know that in general, linear velocity, remember, is, I put an S in there, sorry. Our tangential should be a T, is going to be their distance traveled in the amount of time. So our arc length in the amount of time. All right? And we know that omega is our angle traveled in the amount of time. So, if my arc length is theta times r per time, and I collect my theta and my t together for r, and I notice that theta over t is just omega, we find that our tangential velocity is related to our angular velocity in this way. That the tangential velocity is equal to the angular velocity times the radius. Right? So recognizing that tangential velocity, our linear velocity is our distance per time. In the case of a circle, our distance is our arc length per time. Our arc length, we know, is theta times r. We already talked about how we got that. And then we kind of do a little reorganizing to recognize that theta per time is omega. All right, so we have our how fast, and we have our how far. So I'm going to put those up here so I can make a little more room to talk about that last piece. So how fast is omega per time? That equals W. And V tangential equals WR. All right, so what was the last piece? Well, what happens if we change, if we speed up, we get faster and faster and faster moving around the circle? If I'm having this little piece, instead of it going around at a constant rate, constant velocity, I start spinning it faster and faster and faster. I change its angular velocity, or I start to slow it down, slower and slower and slower. Well, that is just like with our translational motion, that is our angular acceleration. All right, and our angular acceleration is related to just what our translational acceleration looked like. Angular acceleration is how fast is the velocity changing as time goes on, okay? Am I getting faster and faster, or am I getting slower and slower? Is my velocity changing as time goes on? Well, our velocities are angular velocities, so it's our final angular velocity minus our initial angular velocity over time. Just like it was our final velocity minus our initial velocity over time for translational motion. So angular acceleration, and we're only going to look at cases of constant, just like we did with translational, constant angular acceleration. This relationship we define as alpha, lowercase alpha. So for constant acceleration, our angular acceleration is defined as alpha. If I do a little bit of rearranging of this equation, we find that, so if I multiply both sides by t and then add my initial angular velocity, I get my final angular velocity is equal to my initial angular velocity plus alpha times time. Now this should look very familiar. It was one of the relationships we had in the translational world. So instead I'm looking at translational velocity, and I turn all my angular velocities into translational velocities and my angular acceleration into translational acceleration. We see a parallel to our powerful equations that we use for kinematics. So the relationships that we've used in kinematics also work in the world of rotation. We can see that pretty easily in our calculation for angular acceleration. If we think conceptually about what angular acceleration is, our final angular velocity minus our initial angular velocity, our change in angular velocity over time, and we're going to call that alpha. And a little bit of rearranging gives us a relationship that looks strikingly familiar to the ones we use for translational velocity. So what about the other ones? Let's see if another one works. We had a relationship for constant velocity. If you recall, if an object was moving at a constant rate, that relationship was, so if I go constant velocity, we had final position was equal to initial position plus, I do not like this, well, hopefully you can see this, plus initial velocity times time plus 1/2 the acceleration times time squared. Now, for constant velocity, there's no acceleration, so that term goes to 0, and I'm going to change color because the squeaking is driving me crazy. So that relates to x final equals x initial plus, now, if it's constant velocity, v initial is just the velocity. Here, this one's squeaking now. Times time. So again, like I say up here, this is constant velocity. I'm not using that one either. Put them over there. All right, green seemed to work good, hopefully. Okay, so what does this relationship tell us? I'm going to use the simple constant velocity scenario to go through this again. Well, it tells us that if I want to know where I end up, what is my position at some point in time, I have to know where I started, and I have to know how fast I'm moving, how fast I'm changing my position, and how long it is. This, remember, is the position acquired in the amount of time I'm looking at. How much position did I change by in the amount of time I'm looking at to go from where I started to where I ended? Well, I'm rotating. there's a very easy parallel with that. I'm starting at some angular position here on the circle, okay? So I'm starting at some angular position, theta. Our angles are on thetas, and again, remember they're radians. And I'm rotating, I'm going through a rotation. Maybe it's a partial rotation, maybe it's a full rotation, who knows? I'm rotating for a certain amount of time. And how fast I'm rotating for how long I'm rotating is going to tell me how much angle I go through. How much angle I go through. So my angular velocity times however long I'm doing that angular velocity is going to be my angle acquired. So if I know where I started on the circle, and I know I rotated for a certain amount of time, which acquired a certain amount of angle, then I know where I end on the circle. And again, we have a parallel between our translational motion and our angular motion. So as it turns out, all the equations that work translationally that we kind of developed work in the angular world in a one-to-one parallel. So this was the second one. We got the acceleration one. And we can also translate this longer, more powerful equation for position into the angular world. So let's do that. I'm going to erase this one. And we'll go through that really quick. And then we will have the mini lecture be done, and you can look at the next lecture on the practice problem for an example. Okay, so if I have my position where I want to know where I end up in the linear world, remember I have to know where I started. And then we had this combination of knowing how fast I was going at the beginning and how much that velocity is changing by. So this was that really powerful equation that we really kind of use a lot. So it translates one-to-one to the angular world, such that our final angular position is equal to our initial angular position plus our initial angular velocity plus 1/2 our angular acceleration times time squared. So where I end up depends on where I started, depends on my initial speed at the starting point, and then how that speed changes over time in that same way. So that's the most powerful equation, reminding us of the other equations that we've used. We had our final velocity. Whoops. I'm going to do it in angular. Our omega, grief, final velocity is equal to our initial plus our angular acceleration times time. And there was that third equation that used the squares, and that was a combination of these two, removing time from the relationship, and we ended up with v final squared is equal to omega initial squared, omega final squared was v final in translational motion, plus 2 times alpha times delta theta, so our displacement. So these three equations look strikingly similar to our translational kinematic equations, and we can take everything in our whole process, and we'll do a practice problem on that, but our whole process that we did for translational kinematics and use it in rotation. All right, good job.